All right, so last time we used the table to solve limits. That's one of our tools now. We also looked at a graph. That's another way the AP test is going to test you on how to solve limits. And another way is more analytical, where we can just use some different techniques to solve the limits instead of using a table or something more visual. And one of those ways is the algebraic properties, and the other one is using direct substitution. So we're going to start with direct substitution, and then we'll move to the algebraic properties. All right, let's begin. So there is a really easy strategy to solving a lot of limits. If our function behaves nicely, now what do we mean by nicely? That's kind of vague. We will talk about it. It's called continuity, but we're not there yet. So for now, all of our functions are going to behave nicely, but eventually they won't. But if they do behave in this continuous, nice way, what we can do is whatever value our x is approaching, we just plug in that value into our x's. That's called direct substitution. Direct substitution. And it helps us solve a lot of limits. And it's very easy, and it helps us a lot. All right, so let's go ahead and do a few examples. All right, so let's take a look at this one right here. This function, I'll just let you know right now, just to practice, behaves very nicely. It's a polynomial, and polynomials are continuous. What we can do is we can just go ahead and plug in the value that we're trying to get really, really close to on the x-axis, 2. So what we're going to get is 2 squared plus 3 times 2. This is going to equal, 4 plus 6, which is 10. And that indeed is the limit as x approaches 2 of x squared plus 3x. That is a really nice and easy way. That is the power of direct substitution. Let's go ahead and do another one. The limit as x approaches 1 of x squared plus 1 over x plus 2. I'll just preface this right now. On almost all points, it is continuous, except for one point, but we'll talk about that later. And what's happening is that we can use direct substitution because it behaves nicely near x equals 1. So we plug in our numbers into where there are x's. And what we get is 1 squared is just 1 plus 1 is 2. And then 1 plus 2 equals 3 on the bottom. So our solution is 2 thirds. All right, so now let's do our little remark. There are times where direct substitution will not work, and we'll need to find another strategy. You will see that when you get a 0 over 0. And there are techniques to get around this 0 over 0, which we'll talk about soon. But for now, all of our functions won't give 0 over 0. But when they do, doesn't mean the limit equals 0. It doesn't mean it equals infinity. We need a new technique to get around 0 over 0. This is something we call an indeterminate form. We don't know yet. We'll talk about that later, though. All right. Go ahead and try and solve these 3 limits and come back for the solution. They're all behaving nicely, so direct substitution will work. All right, welcome back. So if you go ahead and plug in the numbers that are in where the x values are getting really close to and use direct substitution, you will get 13, 4, and 2. All right, another technique we can use is if we know some more simple limits, we can figure out a lot of different limits because the properties of algebra actually work really well with limits. So let's just pretend we have a function f of x. And as we get really, really close to some value a, f of x gets really, really close to L. That's what we're saying right here. And try and read this one. As x gets really close to a, g of x ends up getting really close to L. So, what can we say with these things? If we have these two properties, then if c is some constant, as x approaches a, c times f of x is just going to be c times our limit L. So if we know what f of x is, we can just multiply the answer to the original f of x limit and just multiply c to that. And then with addition, if you're adding two functions, it doesn't change anything. We are just going to add the two limit solutions. Same with subtraction. Multiplication as well. It's just L times M. So if we know information, we can start to piece together some trickier limits just by multiplying the answers that we already got. Division works as well. This would become L over M. But to preface this, of course, you can't be divided by 0. So M can't equal 0. All right, let's take a really quick example. F of x equals 4 as x approaches 2, or f of x gets really close to 4 as x approaches 2. And as x approaches 2, g of x gets really close to 3. So we're trying to find this limit right here, but what we know is we can use the algebraic limit laws to make this a lot easier on us. What we know is that this function f of x equals 4 as x approaches 2. So we can just add that limit. And then g of x goes to 3 as x approaches 2, but because there's a constant in front, we can use this property to just multiply that constant times our limit. So it's 4 plus 2 times 3. And that's going to give us 10. And that's our answer. All right, and next time we'll look at some of the ways to get past the 0 over 0, but this is a simple way to use direct substitution on algebraic limit manipulation, algebraic limit laws to solve more limits.